Hey, welcome everybody. And it was a great pleasure to see you all back in Cannes last week. Unfortunately, we will have to continue with this kind of hybrid mode with online lectures in the same format as we're doing now. Now, the topic this week is a continuation of where we left last week. And we are going to deal with the optimization problem, which is at the heart of essentially all machine learning methods. And the first thing we're going to do today is to revisit a little bit the topics on logistic regression and some of the basic equations. And when we are done with that, we are going to spend most of the time today on different ways to optimize the cost functions which we have. And in the optimization, we will need to calculate gradients. We want to drive these gradients to zero. And we are going to look at the different schemes by which we can calculate the gradients to a given precision. Now, we are going to encounter methods like the simple gradient descent. We are going to look at a modification of that, which is called the steepest descent, which leads to the family of conjugate gradient methods with some refinements. But these methods normally require that we are able to evaluate the gradient for all data points which we have. This normally becomes, from a computational point of view, when we are looking at systems or methods like neural networks, where we have huge dimensionalities. These are going to be less efficient methods. And some of these methods require that we will be able to invert a high dimensional matrix. And from a computational point of view, this becomes not feasible. And we are going to look at strategies by which we can approximate many of these calculations with simpler methods. And that leads to the whole family of gradient descent methods, stochastic gradient descent methods, and then approximations of a parameter which we are going to introduce, which is called the learning rate. And we are going to discuss these things in more detail. Now, this sounds like not a very exciting topic. So gradient optimization and convex optimization problems sound like a kind of, not exactly a triviality, but a not too exciting topic. However, it is a central topic in machine learning, because when we are trying to find the optimal parameter which describe the data, given a specific cost function, then we have to calculate derivatives, and we have to optimize the calculation of the derivatives, and we have to find the optimal parameters through an optimization process. So optimization and these kind of gradient methods, they really lie at the heart of essentially all machine learning methods. The steps which we are going to take today will also be important for the evaluation of neural networks and deep learning methods. So when we are setting up a neural network, we actually have to calculate gradients. And the way we calculate these gradients in the most efficient way is something which is a big topic in machine learning, essentially because this is where we spend most of the CPU cycles. Now, let me quickly remind you of what we did last week. So one of the things we did last week was to introduce logistic regression. Now, logistic regression is different from the standard linear regression in the sense that the function which we believe, which approximates the data, is no longer a continuous function, but is actually a probability distribution, which is also continuous, but it's now going to represent specific outcomes. And typically, we end up with discrete outputs. So when we looked at linear regression, we had an assumed continuous variable, and we assumed that there was a continuous function which described it, which means that this function in principle could take values from -infinity to +infinity. But when we are dealing with classification problems, and the simplest one is this true-false problem, or normally what we call a binary problem, where we can translate true and false, yes and no to numbers like 0 and 1, -1 or +1. In that case, what we have is a discrete output, and we want to find an algorithm which describes this data. And that led to logistic regression and classification problems. Logistic regression is perhaps the simplest, one of the simplest possible methods we can think of. And again, if that does a job for us, there is no reason on going into more complicated methods. So as an example, if ordinary least squares gives the best fit compared with ridge, lasso, or more complicated kernel regression methods, then we would stay with the simplest possible method. And similarly with the classification problems, if logistic regression does a good job, there is no reason of introducing complicated methods like deep learning methods or other ones. Logistic regression serves here also as a stepping point or stepping stone towards neural networks and the calculation of derivatives and gradients. So we will see now that, and as we saw last week, that the equations which we get, they are no longer linear in the unknown parameter beta. When they're no longer linear in the unknown parameter beta, what we typically do then is to solve the equations which find the optimal values of the parameters. We solve these equations in an iterative way. And this is what we are going to discuss today in more detail. So just to quickly remind you of some of the things which we saw last time, I'm going to bring up the equations because we saw that typically if we were to make a linear fit, what we would then get would obviously be a continuous function, whereas we would like to have, in the binary classification case, we would have outputs that if y of I is larger than 0.5, then we could classify it as a true, and if it's less, we would classify it as a false. And we define them, so I'm just going to go through some of these calculations. We define a probability, which is given by what's called the logistic function or the sigmoid function. You will find different names of it. So logit function, logistic function, sigmoid, etc. And this is meant to represent a likelihood. And we will typically then assign for a category with the output equal to y, we would assign it this likelihood. And for y of I equal to 0, it will simply be 1 minus p of t. So this is a very simple function. And when we look at the value of it, what we would say then is that if this function outputs a value less than 0.5, we would then produce an output which is equal to 0. And if it's larger than 0.5, we would produce an output which is equal to 1. So this function is scaled to live between 0 and 1 as outputs. There are examples of functions. I'm not going to bring up everything again here. What we did was, however, to use in the order to define a cost function, we would then calculate we use the maximum likelihood estimation principle, which assumes then that there is a probability distribution. And this is given by the probability of having a true output, which we label as 1, and a false output, which we label as 0 in this case. And you see now that in case y of I is equal to 1, it's this term which gives us something different from 0. And then in case y of I is equal to 0, then it's this term which plays the role of the probability. And then instead of calculating the derivatives of these functions, we took the log of this function, and that defines our cost or loss function. And in this case, this quantity is actually called the cross entropy in the literature. And then what we did was to calculate this function here and calculate the derivatives. And we can also add regularization terms like we did with ridge and lasso regression if we wish to. So we can always add this kind of hyperparameters to the cost function. And in this particular case, what we ended up with in the simple model which we looked at, we had two unknown parameters, beta 0 and beta 1 in the exponential here. We can have more parameters if you want to. You can make this much more complicated, but we tried to stay with the simplest possible set of parameters. And we assumed that there were basically just two features. If you have something like 30 features or 50 features, then you would have more parameters here, which then would accompany every specific feature which you have. And when we then looked at the negative log likelihood, then we ended up with a minimization problem. And when we calculated the derivatives, we took the derivative of that cost function with respect to the parameter beta 0 and beta 1. And with these derivatives, we can then find a general expression for the gradient of the cost function. And these are the quantities which we want to drive to 0. And now you see that compared with the linear regression, the expressions which we have are no longer linear in the unknown parameters beta. And that means that we, unless we are extremely lucky and have a specific cost function, we will not be able to find nice analytical expressions for the parameters beta. And that's why we have to recur to numerical solutions. Now, coming back as a small aside to linear regression, one of the nice things with linear regression is that we have analytical expressions for the parameters beta, but also that we have gradients which are easy to calculate, so that when we are going to set up the gradient methods in order to calculate these derivatives and to find the optimal parameters, we have an example which we can check against, which gives us analytical results. And that's something which is extremely useful when we're going to play around with different gradient methods. So we can summarize this and we can rewrite the derivative of the cost function, this specific cost function, which is called the cross entropy. That gives us a derivative which is now given by the design matrix transposed times the output, which is discrete, remember that. And then we have this probability, which is the probability of y of I with a given x of I and parameter beta. You can also show that the second derivative is given by the transposed design matrix multiplied with a matrix which has only diagonal elements, which is then given by the product of the probability of true and the probability of false. And then again multiplied with that quantity. Now, since the probabilities are always larger than 0, and this x transpose times x is a matrix which we have seen before, is a matrix which is positive definite or semi-positive definite, then this problem here leads to a convex optimization problem, which is going to have a global minimum. So there is indeed a global minimum in this case as well. So logistic regression and linear regression are pretty similar methods, except that now, instead of having a function f of x, which we believe exists, now we believe there is a probability, p of x. We don't know this probability, and then we make a model for that probability. And in this particular case, this probability distribution is given by this sigmoid function. Now, you can do more advanced things like Bayesian logistic regression, where you would be able to estimate a form for this probability distribution using Bayes' theorem. But that's beyond the topic of this course. So these are the expressions which we have, and you can extend this to more predictors or more features, and then you would simply have more variables which you will need to fit. You can extend this to more classes, and that leads to what's normally called the softmax function. And the softmax function is very much motivated by physics, where we would have the ansatz which Planck made in order to reproduce black body radiation. And this function, the so-called softmax function, is a function which is used when you include more classes. And it's normally defined in this specific way here, where K is one of the classes we're looking at with a given X here, and then we will simply have a normalization constant, which is down here. So this is typically the kind of function you will encounter when you're dealing with classification with just more than one class. Now, the thing we are going to look at now is we are going to come back to these examples. Now we are going to dive into the optimization part. And that is the main topic today. And it's also going to be a topic which we will discuss next week as well, before we begin with neural networks. And the reason why we're going to pay quite some attention to these topics is simply due to the fact that calculating gradients and doing the optimization is really at the heart of every machine learning algorithm. So what I'm going to do now is actually to switch back after these kind of reminder of what we did last week. I'm going to switch back to the Jupyter Notebook, No, sorry, not the Jupyter notebook, but to the whiteboard. And we are going to go through some derivations, and we're also going to look at the some of the simpler methods, what they actually entail, and then we're going to jump a little bit back and forth between the whiteboard and the Jupyter notebook. So I'm just going to switch here to the whiteboard and go through some of the basic mathematics which we need to look at. Okay, so the optimization part, which we will be looking at, is now going to be given by the following derivations here. So let me just quickly repeat the equations which we had for the derivative with the cross entropy. So we defined this cost function for classification, which we call the cross entropy. And what we found last week is that the derivative of this quantity with respect to the unknown parameters is given by the sign matrix transpose times y minus p. This is the quantity we want to drive to 0. And in the particular case which we looked at, we had a problem with two parameters. We had a beta 0, and we found that that one could be rewritten as an I equals 0 of n minus 1. When we performed the derivations, we had y of I, and then minus p of x of I, which is our model here. And let's just label this as G0. So that's the gradient for the parameter beta 0. And similarly, what we had was a derivative with respect to the parameter beta 1, which then was simply given by minus I equals 0 to n minus 1. And then we had x of I, and then y of I minus p of x of I. And this p is what we normally label as the sigmoid function. And this is a quantity which we can label as a G1. This is the other derivative or the other gradient. And we want to drive both of these to 0. Now, as we said, these equations depend, due to the probability here, which we have introduced via the sigmoid function, they depend in a nonlinear way on the unknown parameters beta 1 and beta 0. So the other thing which we need to remind ourselves about is that p and y, they have length, they are assumed to be real, and they have length n. And this x of t is now our design matrix, and it has dimensionality p times n. X has dimensionality n times p. And then we also calculated the second derivative, which I'm just going to repeat here, and that's given by x transpose times this matrix W, which has matrix elements only along the diagonal. And we are going to call this matrix for a matrix H, which is normally called the Hessian matrix. And this matrix W has only diagonal elements, so Wi. These are the only non-zero ones. It's given by px of I, or 1 minus px of I. Now, let's take a look now. Before we move on, we can revisit this topic in a slightly different way, because we are now going to look at the optimal parameters beta, and we can think of now Taylor expanding the cost function in around the optimal parameter beta. So we are now looking at how to find the optimal beta. So we know that in order to find the optimal betas, we have to drive the gradients to 0. So let's now assume, on the other hand, that we perform a Taylor expansion. So we make a Taylor expansion of the cost function, Taylor expansion of the cost function of C of beta around the optimal value. after we have performed a given number of iterations. So we make a Taylor expansion around beta hat, and we are going to have beta hat minus beta of n, where n is going to indicate a given iteration, because now we are going to solve these equations iteratively. But let's assume that we just perform this kind of expansion. And I'm going to, in order to simplify the notation now, I'm simply going to replace the beta hat, so I don't need to carry with me too many symbols, with just a beta. In principle, this is going to be the value of beta after n plus 1 iterations. So this is going to be the converged result. And typically what we're going to assume is that if we now take the vector beta n plus 1 minus beta of n, and we calculate the norm 2 here, we want this to be smaller than a specific parameter delta. And this can be something like 10 to the minus 8, or even a smaller number. So we are going to solve these equations iteratively. And for every iteration, we are going to compute the difference between the two vectors, the one for the next iteration and one for from the previous one. And then we're going to compare this difference with a small number, which we have defined as our convergence criterion. So this is actually, this number is now our convergence criterion. So if we now write this Taylor expansion, so we would now have a C of beta, and keep in mind now that I am using this shorthand for beta hat. So I use beta just. Hope that doesn't cause any confusion. So this should actually be C of beta hat, which is also going to be C of beta of n plus 1 after n plus 1 iterations. But I'm going to keep the C of beta as just a simple way of doing the expansion. And this is going to be equal to C of beta of the previous iteration. This is just a constant. We know how to evaluate that one because we have the previous value. And normally we start this iteration with a guess on beta. This could be random numbers, or it could be an intelligent guess based on our insights about the problem, or it could even be set to 0. That's also possible. And then we are now going to have the next term, which is going to be the gradient calculated at the iteration n. So this is, since these are now vectors, I'm going to have the gradient at iteration n. So if you go back to the equations which we have here for the gradient, g0 and g1, these are going to be calculated at every iteration with a given value of beta. And you're going to see through this why we don't want to calculate, for instance, these gradients exactly when we are going to a high-dimensional problem, because then these gradients will contain many variables and we may have many data points. So let's also look at the next term which we have here. So we should then calculate beta minus, this is a vector, beta minus beta n, like that. The gradient has the same dimension as beta. Then we get the second derivative plus 1/2. And now we have a beta. Since these are vectors and matrices, we have to be a little bit careful. This is a transpose. And then we have the second derivative of the cost function. So the first derivative is just a gradient, which we have plugged in here. But then the second derivative is this so-called Hessian matrix, which we have, which I'm just going to label H. So we're going to have a matrix H. And this is again multiplied with beta minus beta of n. And then we have the higher order terms. Now, what is common to do now is actually to truncate to second order. Because if we go to third order, we need the third derivative of the cost function. And that's going to be involved because it will contain many more complicated operations, and we would like to avoid that. So we're going to truncate the Taylor expansion to this at the level of the second derivative. Furthermore, we are then going to introduce a new parameter. So this is a new vector, which I'm going to define as a beta minus beta of n here. So that means that I'm going to have a slightly simpler expression, and I'm going to terminate it at second order. So I'm going to have a c of beta, and then I have a constant c of beta of n, which is just a constant, and I'm going to label this as a c0 plus the first derivative term, a beta of n, multiplied with this vector, and this vector is going to have a dependence on n, so it's going to be a b of n here. And then I have the next term, which is just, so we put an approximation sign, plus 1/2, and then we have this b transpose of n multiplied with a Hessian matrix, which is evaluated with a value of beta of n, and then this is multiplied with b of n. So this is now our cost function approximated to the second derivative, and Taylor expanded around the difference between beta, the optimal value, and the previous iteration. Now what you see here is that this is of the following form. This is of the form, and now I'm going to rewrite c of beta in terms of a function f of x. So f is now the function, the cost function. It can be any function, and x is a vector, and this contains a constant c plus a gradient transpose times x plus 1/2 of x transpose times a matrix A, where A is actually the Hessian matrix. So the only thing I've done now is just to try to generalize this expression. So x is the unknown quantity, in the same way as b was the unknown quantity in the previous equation. So x is the unknown. Now, what our problem corresponds to now, when I take df of d of x, when I take the derivative of that, and these are matrices, and we want this to be 0, this is the same as saying that a times x plus g is equal to 0. And that means that we have a problem which we have seen many, many times before in linear algebra. We have that a times x is equal to this quantity minus g. And in our case, g depends on the gradient at a given iteration. So in our case, g of n is actually g calculated at the beta of n. This quantity here is the Hessian matrix calculated for a value of beta of n. That's the previous iteration. So A, this matrix A, which we now wrote in as a more general matrix, is in our specific case with the cost function, that is actually the Hessian. Now, when we now look at this specific case here, we also have that x is going to be beta minus beta of n. So I just wanted to bring up some kind of generalities here. What we have when we are solving this equation here, this specific one, this is an equation which we, obviously, if we can invert the matrix, then we know that x is equal to a minus 1 times g here. That's just a standard linear algebra problem. Now, what we would have when we are now setting up this kind of iterative scheme is, if you now look a little bit closer at the equations, this type of problem is a type of problem which we would then solve iteratively. So what we would do then is actually to define an x of k plus 1. No, sorry, not that notation. When we solve it iteratively, we're going to have an n plus 1, and this is going to be given by x of n minus. And then in order to solve this type of equations iteratively, we have the inverse of the matrix, A minus 1, calculated at iteration with a value x of n. and this is multiplied with a gradient calculated at iteration n. So this is the standard scheme which we get when we are setting up the Newton-Raphson scheme for calculating the update of the quantity in an iterative way. So in our specific case then, if we now look close at the equations which we have, this means that we would have a beta of n plus 1, which is actually equal to beta of n minus the Hessian matrix inverse calculated at a beta of n, and this is multiplied with g of n, which is then evaluated at beta of n. So these are the equations which we are going to evaluate when we now look at the iterative procedure for finding the solution to this type of equation which you see here. So this is nothing but an iterative way of solving this type of equation. Okay, so we have a set of equations which we want to solve. And one of the things which strikes you immediately is that we have to calculate the inverse of the matrix. But we need also to calculate the gradient. So we need the gradient, g of n, but we need also to invert a matrix. And clearly, if you now are having something like a neural network calculation, you could easily have 1,000,000 parameters beta. And this number of parameters beta, which we would have in a neural network calculation, means that we would have to calculate 1,000,000 gradients. And if you're having something like 10,000 data points, you need then to calculate 10,000 gradients for 1,000,000 parameters. And no, sorry, if you have 10,000 data points, your gradient would involve the 10,000 data points, and you have to evaluate 1,000,000 gradients. Now, your matrix H, if you have 1,000,000 parameters, is a matrix of dimensionality 1,000,000 times 1,000,000. But even with a smaller case like this Wisconsin breast cancer data, which we mentioned last time, which has 30 features, even for such a small case, this matrix is a 30 by 30 matrix. It's a 30 by 30 matrix. We have 30 parameters, which means that we need to calculate 30 gradients. And a typical calculation involves something like 100 iterations. So if we perform 100 iterations for 30 parameters, it means that in total, we have to calculate 100 times 30. We have to perform 3,000 iterations. Now, for every such iteration, we have to evaluate 30 gradients, which includes something like 500 data points. And at the same time, we have to evaluate a 30 by 30 matrix and take its inverse. Now, this becomes quickly time-consuming. And what is common to do then is actually to replace this quantity here, h minus 1 of beta of n, with a constant. And this constant introduces a new parameter in machine learning. So it's actually, you're going to see that's actually going to be, from a computational point of view, it's going to be cheaper to evaluate over a grid of values for this learning rate than to calculate the gradients and the inverse of the matrix. So we replace that one with a parameter, which is in the literature called the learning rate. And we are going to call this gamma of n. So this learning rate can be made to be something which we can tune iteration by iteration, or we can just keep it as a constant. So that means that we are going to have two main topics which we have to deal with. So the two main issues, when we have replaced the second derivative with a parameter which we can tune, So one is the evaluation of the gradient itself. And here, what we have are essentially two main methods. One is called the simplest gradient descent, which we're going to encounter quickly. Then we have something which is called a stochastic gradient descent, where we actually perform smaller evaluations of the gradient for smaller batches of data. And then we compute these smaller batches of data because they are cheaper to calculate. You spend less CPU cycles when you calculate the gradient for smaller amounts of data than just calculating the full gradient. As we will see for linear regression, the gradient is going to involve a matrix vector multiplication. And vector matrix multiplications, they are CPU intensive. And if we can reduce the dimensionality of the vector matrix multiplication in smaller batches of data, this is actually something which is going to lead to less CPU cycles. So a standard method is called a stochastic gradient descent. And I'm going to put acronyms here. So I'm going to use, when I use GD, that is going to be the brute force gradient descent. And I'm coming back to what that means. And the stochastic gradient descent is normally written as SGD. And then we are going to have GD or SGD, and there are ways to speed it up. And one of the ways to speed it up is called momentum gradient descent. And we are coming back to what that means. So this is one main topic. So let's call this topic 1. And then the other topic is an optimization of the learning rate. Optimization of this parameter gamma of n. So this can be done in many different ways. And these two combined, if you can cook up something really, really smart, as I mentioned when we met last time, you would be getting many more friends. And these are friends which will cite you, because this is really one of the bottlenecks of the machine learning approaches. And as I mentioned last time, there is an algorithm which is called ADAM, which was presented in 2014, which has more than 120,000 citations. So the optimization of gamma. So we have ways to optimize that. And one is just to have a simple schedule. You can have a linear, an exponential schedule. We normally call these different schedulers, where we adapt the learning rate according to a specific iteration number. Different schedulers, and these are normally pretty simple ones. They don't involve any information about the gradients, no gradient info. And then, if we now look at the more advanced ones, so what we have is adaptive learning rates. And in this specific case, what we're going to meet is something which is called ADA-grad, adaptive gradient. We're going to meet another method, which is called root mean square propagation, or just RMS prop. And then we have a final method, which is also widely used, which is called ADAM, adaptive gradient with momentum. These are ways by which we are going to update this learning rate. Now, so what we are saying now is that this learning rate, gamma of n, is going to replace the Hessian matrix. So this should be the inverse of the matrix calculated at a given iteration of beta of n here. Now, if we look at that expression for the simple example which we had before, the logistic regression case. So for logistic regression, this matrix with only two parameters with beta 0 and beta 1. This is something which we actually can consider evaluating fully. So with these two parameters, what we have is that this h of beta is given by a matrix, which is actually nothing but the Jacobian matrix, where we have the gradient for d0 for 0, so beta 0. And then we have the gradient g0, which we defined in the beginning of the lecture today, and beta 1. And then we have g1 with respect, derivative respect to b0. And then similarly, we have g1 derivative with respect to beta 1. So if you only have two parameters, you can actually consider evaluating this one for every type of every iteration. Now, there are many ways to solve this. So if we do a Newton-Raphson calculation, then we're actually calculating the Hessian matrix. And we are computing the second derivative, and we are introducing that one and performing the matrix inversion. That is going to be quite time-consuming when we come to problems with many, many variables. So as I said, if you're dealing with the Wisconsin cancer data, this is going to be a 30 by 30 matrix. If you're doing a DNA sequencing where you want to find which features of the DNA are the important one for, let's say, one specific type of tumor, you can easily end up with hundreds of thousands of features which you want to examine. And then your Hessian matrix is basically impractical to invert that matrix. So what these different methods deal with are actually ways to, one, evaluate the gradient in an efficient way. And that's normally done either by gradient descent or by stochastic gradient descent. Then, or with variance, with so-called momentum addition. And then we have the optimization of the learning rate for every iteration. So what we are going to do then is actually try to fake the way the learning rate gets changed from iteration to iteration. So essentially, these are the kind of overarching picture, is the overarching picture which we are going to deal with. Now, let's look at this Taylor expansion which we made. And let's now assume the following. So we are going now to assume that we are going to make a new Taylor expansion just to illustrate how we could find an optimal learning rate. The reason why I'm putting this up is that this simple Taylor manipulation is going to give us a kind of hint on what kind of inputs we can give to methods like ADA-grad, which we have here, or root mean square propagation, and ADAM. So let's just still try to stay simple before we take a small break. And let's Taylor expand the cost function again. And now we are going to make a Taylor expansion of the cost function around a value beta of n plus 1 minus. And now we have computed the grade. Sorry, it's not that one. This is the new value. So remember now, let me just take this out first. So we have that beta of n plus 1 is equal to beta of n minus, and then we have this learning rate gamma, which we now leave without a superscript n, and this is multiplied with the gradient at n. This is now the approximation which we are making up here. If you look at this approximation which we put here, we are now simply replacing the matrix H with a learning rate, which is a new parameter. So what you see here is actually the standard gradient descent, GD. So we Taylor expand around this value. So that means that we look at the Taylor expansion of beta n minus this gamma, and then we have the gradient. And this is obviously going to be equal to C of beta of n. So this is just a constant. And then what we're going to get then is minus, obviously, because we have a minus sign here. So there's a gamma. We have the gradient transpose of n multiplied with the gradient. And then we have plus 1/2. And now we have gamma squared instead of the Hessian matrix. And then we have G. So we are now looking at this term which comes here squared. So we have a G of t at the iteration n. We have the second derivative of G of t, G of n. And then we simply approximate this to the second, at the order of the second derivative. Now, what we assume now is that C of beta of n is not a function of gamma. And we simply now calculate the derivative is not a function of this gamma. So what we do now is simply to calculate the derivative of dc with respect to gamma. And if we do that, then we know that since we have assumed that this function is not a function of gamma, we are left with then gamma multiplied with this quantity. So this taking the derivative with respect to gamma simply gives us minus G transpose times G. And here we get a factor of 2 times gamma. So we want this one to be 0. And that means that we have gamma is now equal to G of t iteration n, G of n, divided by G of t iteration n of h times G of n. And h is also calculated at iteration n. So this is actually quite interesting now, because this gives us a hint on how we could approximate this quantity. And you will see that when we now bring back this root mean square propagation or ADA-grad, there will be approximations which are based on this type of equation. Now there's an interesting case here. If G is an eigenvector of H, so if H times G is given by lambda times G, and we also assume that G times G is normalized to 1, what we see then is that this gamma, when we plug it in, is simply going to be 1 divided by the eigenvalues of gamma. So lambda is now the eigenvectors of the Hessian matrix. Lambda, is an eigenvalue of the Hessian matrix. So if we can diagonalize the Hessian matrix, we can actually try to use that as a way to set the learning rate. And we know that the size of this matrix, the size of the learning rate is then given by the maximum value and the minimum value. So that means that the smallest learning rate which we can call gamma min, is obviously given by 1 over lambda max, the largest eigenvalue. And remember also that the matrix we are looking at, the Hessian matrix, is a matrix which we have shown is positive definite. So all the eigenvalues are larger than 0. And then gamma max obviously has to be equal to 1 divided by lambda min. In general, what you can show, so I'm not proving this for you, but in general, what we have is the following. The learning rate should be smaller than 2 divided by lambda max. And this is something we are going to practice after a small break now. So it means that the learning rate can take values between the maximum eigenvalue and the minimum eigenvalue, and the convergence rate of the optimization process will depend on where we place ourselves in terms of the range from the minimum and maximum eigenvalues, because they will then define the maximum and the minimum learning rates. So this was just a simple analysis of what is going to come after the break, when we now look in more details into programs and how we can efficiently implement the calculation of the learning rates and how we can use that to calculate the gradients. So I hope the mathematics here wasn't too difficult. I simply stated this without proof, but if you go into the literature, you can actually find demonstrations and proofs of the learning rate having to be less than 2 divided by the maximum eigenvalue of the Hessian matrix. So everything we are going to do now after the break is going to deal with ways to circumvent the calculation of the Hessian matrix, and it's going to deal with ways to simplify the calculations of the gradient. And because these are the true bottlenecks in essentially all machine learning algorithms. In all machine learning algorithms, at the heart, there is an optimization problem. And that means that we have to evaluate gradients based upon the cost function which we have chosen. So I'm sorry for going a little bit over time. I'm going to pause the recording now. So welcome to the second session of today. So what we have found when we perform a simple Taylor expansion of the cost function around the optimal value is that we can, if we want to, we can then find an expression for this learning rate, gamma, which is one of the parameters we are going to deal with in the everything which comes from now and on. We can calculate that one in terms of the gradients and the Hessian matrix. Now, if you look at this specific expression which we have here, this one, this means that we would have to calculate a matrix vector product, and then we would have to calculate the product of the inner product of two vectors. And these are obviously quantities which are time consuming. Now, clearly, this becomes a scalar when we do the calculations, and this becomes also a number, which means that we simply have a number divided by another number. However, to evaluate, let's say, a matrix times a vector calculation is something which, multiplication is something which is normally time consuming, and we want to avoid that. And that is going to lead this feature of us wanting to avoid dealing with these kind of evaluations is going to lead to different ways by which we can schedule a change in the learning rate as we move on iteration by iteration. Now, the thing we need to think of also is that this learning rate is a quantity which we cannot put to any kind of random value. And you can easily see that when we now look at the simpler case. So suppose now that we are dealing with a one-dimensional problem, and we have a cost function C of beta, and we want to find the minimum of this function. So if we now have a function which goes like this should now be our beta optimal, beta hat, which is our beta optimal. Now, depending on how we choose lambda, we could start at a given position here. So this will be our starting point. So this will be a beta 0. And then depending on the value of of gamma, the learning rate, we could then have, if we have a gamma small, if it's too small, we would just approach the minimum after a given number of steps in a very slow way. And we could actually risk of ending our iteration at a point here. That means that after a given number of iterations, which we would fix as a parameter, we will not be able to reach the final point. Alternatively, if we allow for many, many iterations, we could then reach the final minimum. If gamma is ideal, so let's change a color here. So beta, gamma, this was the case gamma small, gamma ideal, what we would get then could be something like this. So we would start at this beta 0. We could go over to this point, and then we could jump a little bit back and forth till we reach the final point after a given number of steps. if we have the learning rate which is given, or if we can calculate the Hessian matrix, we would actually reach this ideal point in just 1 or 2 iterations, as you will see from the program demonstrations. Now, if we then have, so with ideal, it means that gamma is now between this gamma min and this maximum value, which are typically given by the maximum and minimum eigenvalues of the Hessian matrix. If we, on the other hand, have a value which is too large, so that means that we are choosing now a value of gamma, which is larger than 2 over lambda max. If we do that, then we would have a new case here, gamma larger or equal than 2 over lambda max. And in the programs which we're going to go through now, you will see that if you really play around with these parameters and make it larger or equal to 2 divided by the maximum eigenvalue, you will then see a behavior like this. You will start in this point. You could go something like there. You could go down here, but then it would diverge. And the process would never converge within the number of iterations you have, and you will simply just converge to a, or you will just move on to a huger and huger number. And we will see demonstrations of that in the for the different codes which we're going to look at now. So let's now switch back to the Jupyter Notebook after these kind of preliminary manipulations. I should also mention that what we have put up here, this recipe which you see, is actually the recipe for a method which is called the steepest descent. And the steepest descent is a simpler modification of the gradient descent. So the simple gradient descent which we are going to implement, so the simple gradient descent, simple GD, the way we are going to implement that is to have an iterative process where we have a beta of n plus 1, which is actually beta of n minus just a fixed gamma value, no changes to gamma. And then we are going to calculate the gradient at iteration n, which means that we are using the previous value for the unknown parameters beta. So this is the simplest possible way we can do that. And this involves also the calculation of the full gradient. So this is the full gradient. And just to prepare you for the examples to come, the full gradient, if we now look at ordinary least squares, then the gradient of g of n is going to be given by the design matrix X, which is fixed. And this now contains a y value, which is also fixed. We know the values of it. But then we have to multiply that with the unknown parameter beta. And this is a beta of n. And you see now that what we have is a matrix vector multiplication. And that becomes quickly time consuming. But let's now look at it. Let's see some actual examples here. So we are going to switch back to the Jupyter Notebook. So if we now move into the Jupyter Notebook for this week and also for last week, and if you scroll down here, then you will come to the first examples on the applications of the gradient descent method. So the first part here contains again some of the results we have discussed earlier. And now if you go down here, you will find basically a summary of what we discussed now before the break. There's a reminder on Newton-Raphson's method, which is essentially based on this Taylor expansion. In our case, we are searching for the roots of the gradient. So this function is actually gradient, which means that the function you see here is the second derivative or the Hessian matrix. And the iterative procedure is actually given by that. You will find an extension to more variables where we include the Jacobian matrix, which then defines our Hessian matrix. And then there are some discussions of the steepest descent method, properties of convex functions, and so on. But what I wanted to do now is to actually give you the first examples, besides these methods, which actually all these methods, like the steepest descent, the conjugate gradient methods, they involve the calculation of an inverse of the matrix, or the calculation of the Hessian matrix multiplied with the gradients. And that's something we want to avoid. So if we now look back at one of the first homeworks, which we had in the first time, for the first week when we met, in that case, we were looking at a simple function where we had some random numbers, and then we had our y, which was simply a linear function in terms of the parameter x. And we had some additional random noise given by normal distribution. So if you now look at the gradient descent example, and we just have two parameters, and we want to perform a polynomial fit. So that means that in this case, we keep the intercept, and it means that the design matrix is going to have a dimensionality 100 times 2. Now, you quickly see now that if you have more parameters and you have more features, this matrix becomes larger and larger. In this specific case, with 100 data points, we would have then the following cost function, which is simply now in our case is just the mean squared error. And we take the derivative of this quantity, and we know that the derivative or the gradient of that quantity, this is something we calculate in the very beginning, is now going to be given by, actually I forgot another matrix when I put up the expression. So the derivative or the gradient is now given by this more compact expression, and then you have the individual expressions here. And you can easily see from the expression here, if you increase the number of data points, you have to perform these evaluations many times. And if you increase the size of the number of features which you want to determine, which leads then to a number of parameters, then clearly you have a matrix times a vector, and a matrix times a vector. And these are clearly evaluations which you would like to avoid doing if you have too many features and too many data points. That is going to lead to what's normally called a stochastic gradient descent. So the Hessian matrix, in this specific case, is actually something which we can also evaluate easily. And this is going to be simply, since there is no dependence on beta in y here, when we take the derivative, this term disappears, and we're simply left with the transpose design matrix times the design matrix. And when we did the singular value decomposition, if this matrix is well defined, this will always be a lead to a convex problem. If the matrix has eigenvalues, which could be 0, or if the matrix could be actually semi-positive definite, or if the matrix has only non-zero eigenvalues or non-zero singular values, then it will always be a positive definite matrix. So we can now set up an iterative scheme. We could then do the following. We could choose a learning rate, gamma. So we replace the Hessian with this learning rate, and we could simply put in a parameter. And normally what is done in most calculations is that you have an array of parameters, and you would often do a grid search in order to find the optimal learning rate. You could stop iterating when you have reached a gradient which is smaller than a given quantity, or when the difference between the new value of beta and the previous one is smaller than a given quantity. Now, in the code below here, I haven't included such a stopping criteria. This is just a plain laziness. So this code also compares the result with the analytical result we get from linear regression. So if we now just take away the noise here, let's just do that. And we set up the Hessian matrix as well. And we calculate the eigenvalues of the Hessian matrix. What we can do now is to define this quantity here in terms of the this term, the learning rate. So this is actually our learning rate here, which I call for eta in the code. So in the learning rate, what I'm doing now is to take 1 divided by the maximum eigenvalue. So recall from the statement I made before the break that the optimal value of eta should be smaller than 2 divided by the max eigenvalue. So what I'm taking now is I'm setting up the Hessian matrix for ordinary least squares. So keep that in mind. This is for ordinary least squares. I then perform a number of iterations. So this is done in a very brute force way. There is no stopping criterion except the number of iterations. And then you see now I calculate the gradient. So I have 2 divided by n here. And then I have the 2 matrices which are being multiplied. I multiply with the value of beta. And then I have a value of y here, which has to multiply with xt. And I also give beta a random value. This is my initial values. And if I look at the calculations now with this specific problem which I had, you see now that from the original data, my intercept is 4 and the slope is 3. The first thing I do is actually to calculate the inverse of the matrix and then obtain the parameter beta. So that gives me, by matrix inversion, gives me 4 and 3. And then you see now that my problem now with the correct learning rate approximation gives me the same result as I would get by matrix inversion. Now what I could do now is actually to change this value here, and I could just choose a parameter here and just let's see what happens. So we know that the eigenvalues should be between 0.27 and 4.5. But let's not choose a learning rate, which is 0.1 here, and see what happens. In this case as well, I have a pretty decent result. I haven't counted the number of iterations. If I were to reduce the number of iterations, let's see what happens then. And now you see that when I have reduced the number of iterations here, I'm actually getting a result which is not the exact result. So it means that I need more iterations. Now, if I make the learning rate larger and larger here, suppose I make it 0.0, and let's see what happens then. Then suddenly, as I demonstrated before we went to the Jupyter notebook, you see now that my result doesn't converge. So I've actually violated the limits which I imposed on the value of the learning rate. So if I make a learning rate very, very small, let's see what happens then. If I make it very, very small, you will also see that it doesn't converge properly to the correct values. So in that specific case, I would actually have to increase dramatically the number of iterations. Now, what you're going to see in essentially all calculations is that since we don't know the eigenvalues of the Hessian matrix, so to calculate the eigenvalues, if you have a matrix of dimensionality n times n, then the eigenvalue algorithm normally scales as n cubed the floating point operations. So if you're dealing with neural networks where you have, let's say, 100,000 parameters, you do not diagonalize 100,000 times 100,000 matrix, where you also have to generate the derivatives of the gradients as input to the matrix elements. So you see, basically, from these simple examples, my hope is that you can see the kind of constraints which we have when we deal with these type of problems. Now, this is what we normally would call a vanilla case. It's a very simple case, and we can easily understand what's going on. We can also run the calculations by simply calculating the Hessian matrix and then using that one in the calculations of the gradient. So what you could do now, instead of setting up this equation here, we could now take and calculate, and note as well that in the specific case of ordinary least squares, the Hessian matrix does not depend on the unknown parameter beta. This is, after all, a linear problem in beta. So if I were to do this, what I'm doing now for the standard linear regression, or the logistic regression, I can actually not do this specific operation which I'm setting up now, because now I could actually set up linalg and then calculate the inverse of the Hessian matrix. So what I could do now is simply take inverse of this matrix, like that. And we're not gonna calculate the eigenvalues, we don't need them. And we are not going to need a learning rate either. And we're just gonna set up, let's say, 2 iterations. And now instead of us introducing the learning rate, we simply put in the inverse of the Hessian matrix and simply multiply that with a gradient. And let's see what happens now. And now you see with only 2 iterations and the inverse of the Hessian matrix, we are spot on the final result here. If we put that one to 1, you will see that we get the exact result, because now we do have the exact inverse of the Hessian matrix multiplied with the gradient, and that means we are just spot on the correct result, even if we started with a random value here. So the first iteration was actually a random value, and then this brings us to the correct result. So you see now from these simple demonstrations, you see that if you have a small problem, it can actually be worth calculating the gradient and calculating the inverse of the Hessian matrix and just performing this operation if you do not have an analytical solution, which we do have in ordinary least squares and ridge regression. So I hope these simple examples convey the basic philosophy of what we need to do now. So our main problem is that we don't know the value for the learning rate, so we have to start with a guess. We will typically set up an array of values for the learning rate, and then try to find the optimal result for instance, the mean squared error. So essentially, what you have here is just a simple demonstration. You could use the functionality in scikit-learn instead of writing your own function. I'm not going to repeat this exercise. You can do the same with ridge regression. And in that case, you would have a parameter lambda, which comes in here. And then when you do that, you need to take the derivative with respect to beta here as well. So your gradient now contains a parameter of 2 lambda times beta 0 and beta 1 for this simple case. And this is going to be your gradient, where you now have to include this parameter beta, multiply with lambda. And in general, you could then write a function where you simply invert the matrix which you have here. And you will need to calculate the Hessian matrix again. And in this particular case now, you can see that the only thing you need to think of when you're calculating the Hessian matrix is to specify a hyperparameter lambda. And in this particular case now, the Hessian matrix differs from the previous one in terms of this parameter lambda which you have. So I have 2 times lambda times the values of the parameter beta. And when we do that, we can then invert the matrix. So we have the identity matrix here. We can repeat the same exercise, but now when we set up the gradient, we have to pay attention to the fact that we have 2 times lambda times beta. And then in our case, if we wish to compare with scikit-learn, for instance, we have to be careful whether they include the gradient, the intercept or not. And if we do the calculations here, you will now see that even with a noise which is added, we are basically spot on the results here. If I take away the noise, we will actually be spot on the results. And we will have a correct result, which is 4 and 3. And you can see that comes out here. So the eigenvalues of the Hessian matrix, these are the correct values, 3.993, because now we don't get 3 and 4, because we have a parameter lambda, which now gives us a cost function which is different. So we're actually tuning a cost function now, which now includes also the hyperparameter lambda. So this would be just a simple extension of what we did before. And we can use the eigenvalues. It's a simple baby case, 2 by 2 matrix. But again, as soon as we move over to more complicated cases, there are severe limitations. And this is where the next set of methods is going to enter into play. So gradient descent, it finds local minima of a function. The algorithm is deterministic. If it converges, it will converge a local minimum of a cost or loss function. So in machine learning, however, we are often dealing with extremely rugged landscapes with many local minima, and that can lead to poor performance. So that's one point against the gradient descent, which is so easy to implement. You will also see that it's very sensitive to initial conditions. You may start close to local minimum, but that may not be the minimum you want to reach. So you can end up at different local minima, and that's why it's important to think about how one initializes the training process. The gradients are computationally expensive to calculate for large data sets. And in our case, what we are dealing with, if you're doing linear regression, we are calculating something like this. This is a cost function, the gradient of that. And this becomes quickly extremely computationally expensive. So one of the ways to do this is actually to calculate the gradients using small subsets of the data. And these are normally called mini batches. And that leads to introducing some kind of stochasticity into our algorithm, as we will see pretty soon. The gradient descent is extremely sensitive to the choices of learning rates. And this is actually one of the most important parameters in all machine learning algorithms. So when we are going to set up a code for the calculation of neural networks, what we are normally going to do then is to tune the results as a function of different hyperparameters, like this hyperparameter lambda we use in ridge regression or lasso regression, and the learning rate. These are going to be the parameters which play the most important role among all the set of hyperparameters which we have. And the other thing with the gradient descent, since we are not changing the learning rate adaptively with information about the given gradients, what happens then is that all the gradients which we're dealing with are treated in this parameter space of the learning rate. They are treated in the same way. So that means they grow with a parameter which is given by the learning rate, which will be the same for all directions. So some of the gradients may vary strongly and may need another learning rate than a gradient which varies slowly over many, many integration points. So the ideal scenario is obviously to be able to calculate the Hessian matrix. Now, this matrix is normally approximated in specific algorithms like the modified Newton methods. And there are several methods by which you can approximate the Hessian matrix. But in general, what we normally do is actually to try to use some ways to cheat and avoid to calculate the Hessian matrix or approximations of it by simply finding up a recipe which allows us to calculate the learning rate in adaptive way. Now, there is a method which is called, which allows us to improve the convergence of gradient descent methods, the standard gradient descent. So this is a method which is independent of whether we do a stochastic gradient descent or a plane gradient descent. And this is called momentum gradient descent, or a name which I like is memory gradient descent. And memory gradient descent or momentum gradient descent means that this is a method which keeps track of information from the previous iteration which we did. So that means that if in case your gradient varies strongly from one iteration to the next one, you can soften that by keeping information from the previous iteration. Now, this is a method which is very easy to implement. And I just wanted to show you a very simple example which we have here. And this is a method which now implements the standard gradient descent. It's a very simple function which we have. So just x squared, as you can see here. And the derivative is also pretty simple, 2 times x. Hope you don't get offended if I plot these simple examples. And you can see now the value of the gradient, which is being plotted for every iteration here. So these are the function values and of the gradient. So you can see now that the gradient, this is something which we want now to become closer and closer to 0. So we are reaching this point here. And you can see now from this so-called momentum approach, or this is actually the standard gradient descent, the gradient is getting close to 0 after 26 iterations. So this is the value of the gradient which we are looking at. If you now do this with momentum, where you keep a memory, and I'm going to go through the details just in a while here. So just be patient. So we had 26 iteration. In this case, the gradient is close to 0 after half as many iterations. So I just needed 13 iterations when I keep track of the memory of the previous, from the previous iteration. So next week, I'm actually going to explain to you a little bit more in detail what is going on beyond this momentum gradient descent, and why this normally speeds up. So one of the things which I wanted to bring in before we take a pause today and then meet again next week is to introduce what's called stochastic gradient descent. So stochastic gradient descent, what it actually does is that it allows you to calculate the gradient in a more efficient way. Because what you're doing now, instead of taking your 1,000 points and calculate this for the given number of features, you actually split this up in smaller parts. And smaller parts means that the number of floating point operations which are needed to perform the matrix and the matrix vector multiplications are going to be smaller. And then you will simply sum up over all the data sets which you have, and then calculate the final gradient. So in large scale applications, there's a typical case here where you have millions of data points, is to actually compute the gradient over smaller blocks or batches of the training data. So a typical batch could contain some 1,000 examples from an entire set of several millions. And this batch is normally used to perform the parameter update. So let me quickly say something about this. So in stochastic gradient descent, the extreme case is the case where we have only one batch. That is, we include the whole data set. So that is sometime, this just brings us back to the standard gradient descent. This is relatively less common to see because in practice, due to vectorized code optimizations, it can be computationally much more efficient to evaluate the gradient for 100 examples than the gradient for one example 100 times. You can easily do the mathematics here in terms of floating point operations. So what is normally done is actually something which is called mini-batch gradient descent, which people also call batch gradient descent, or simply just stochastic gradient descent. So sometimes there's a mix of wordings here. And normally these kind of batches are set to values in powers of 2, because many vectorized operations, they actually work faster when the inputs are sized in powers of 2. So when I'm saying stochastic gradient descent, I'm actually going to mean a stochastic gradient descent with mini batches. And that's the kind of standard wording which is used normally. So the stochastic gradient descent is a way to circumvent the calculation or the loop over all the data points in the calculations of the gradients. And the underlying idea is actually to split your gradient now in terms of small blocks. So as an example, just consider you having 10 data points, and then you can choose 5 mini batches. Then each mini batch contains only 2 data points. And these batches are typically, or the starting point here is normally selected randomly. So your gradient now, instead of looping over all the data, is something which is being looped now over the number of batches which you have. So that means that your gradient step would now look like a loop over the batches here, and where you now pick numbers randomly with equal probability. And then you run over all the possible mini batches, and that is normally referred to as one epoch. Then when you've done that, you repeat it. And so it's typical to choose a number of epochs, and for each epoch, you iterate over the number of mini batches. So the typical example you would do this now is you would fix, this is a number of data points, you fix the number of mini batches, and then this gives you the number of mini batches as a number of points. So the size of a mini batch has 5 entries. This gives a number of mini batches, and this is a number of epochs. So for each epoch, you run over the mini batches which you have, and then you compute the gradients. That means that, so a natural question is obviously also where you stop. And one possibility is to compute the full gradient after a given number of epochs and check if the norm of the gradient is smaller than some threshold and stop if true. However, the condition that the gradient is 0 is valid also for local minima. So this would only tell us that we are close to a local or global minimum. However, you could also evaluate the cost function at this point, store the results, and continue the search. And if the test kicks in at a later stage, we can compare the values of the cost function and keep the parameter beta that gave the lowest value. There are many ways to deal with these type of calculations. And the kind of brute force way of scaling your learning rate could be something given by this simple scheduler, which you see here. You can set up an exponential decay for this. You can set up a linear decay if you want to, so that you change the value of the learning rate as you move on in the calculation as a function of the number of epochs. However, as we will see below, this is not very efficient. And the favored method is actually to use some information about the gradients and implement that in terms of a method like adaptive gradient and root mean square propagation, or the ADAM method, which is an adaptive gradient method with momentum added. And this is where I'm going to stop today. So next week, we are going to look at a code with a number of mini batches, which varies. We're going to look at momentum gradient descent and momentum stochastic gradient descent. And we are going to look at the algorithms for adaptive gradient, root mean square propagation, and the adaptive gradient with momentum. These are the methods which people normally implement in all kinds of gradient estimations where we want to find an iterative way of computing an adaptive learning rate, which is not a constant any longer, without having to evaluate the Hessian matrix. So next Monday, we are going to look at these details, and we're going to start with a code for the stochastic gradient descent, as you can see here. So we are going to run over the number of epochs. We are going to place ourselves randomly in a small region, and then that defines my X and Y values. We calculate the gradients for the smaller region, and then that means that the expectation value here is divided by the number of data points we have in a specific mini batch. And then we just keep iterating. And what you will see then when you run this code, so this is the result from the own inversion. This is if we use the Hessian matrix. So the two first ones are just spot on each other. But when we do the gradient, the stochastic gradient descent, you will see now that the result will never match exactly the correct result. We will get closer to this exact result when we now move into the adaptive learning rate. So keep in mind that here, the learning rate is kept almost fixed, except for a simple scheduler where we change the learning rate so it reaches a fixed value after a given number of epochs. But that's a simplified way of changing the learning rate. And clearly these results here will also depend very much on the type of problem we have. If we now take away noise here, then it's normally It's pretty common then that the results become better. And you can see that when we've taken away noise, even the stochastic gradient descent is pretty close to the exact value. Okay, so we're going to stop here today. And we are going to, when we meet next week, we will then discuss in more details these more advanced methods to find an adaptive recipe for the learning rate, which contains information about the gradients. And these are the standard methods which are used in machine learning algorithms.